Then for what I talked about with the potassium hydrogen phthalate, a 780 kilogram lot, there were something like 14,832 or some number like that bottles of 60 grams each of this, from this 780 kilogram lot. Obviously, we could not analyze all of them. Number one, most of those bottles have to be available for sale, but we want to have a representative sample from the whole lot. And to do that, we go to the Statistical Engineering Division, SED, who works with the Technical Division, which is the division that I came from, to make an experimental design saying which ones of these bottles do we pull from the whole set and actually subject to the chemical analysis, because those bottles that you use for analysis, they don't go back to sale because you've used some portion of the bottle. You've got to sell the customer that they bought 60 grams, they want to get 60 grams. A little side joke here that you might not understand unless you're familiar with East German history. When I first saw the acronym SED, I think, this is interesting, because this was the Sozialistische Einheitspartei Deutschlands. That was the name of the Communist Party in the former East Germany. And I came, remember in '73, I went by train across East Germany to get to Soviet Union and back. When I see that, I think of the SAD in the former East Germany. And now having it represent Statistical Engineering Division staff that I'm dealing with seems kind of a little bit humorous. Don't laugh, it's a joke. It's not a joke, it's true, but it's funny. If you have the right attitude, it's funny. Then after you do all this, from the bottles that have been pulled from the batch, you make the primary measurement, for this case for the electrochemical measurement, to determine the certified value that is going to be assigned to the SRM, and either from the scatter of these primary measurements you get the homogeneity of the batch, or sometimes you make a separate measurement of different subportions to determine the homogeneity. But how much, if you have 14,000 bottles, bottle 1 and bottle 358 and 10,392 and 14,800, how different are they? What kind of scatter do you see? That has to be taken into account, because the buyer is going to get bottle 3,906 or 7,235. What's the probability that they're going to be how far off the average value, if you will, that is being measured? The division I came from does the steps in black. The blue steps are done by different staff in different divisions. It goes on. Then you have to calculate the certified value. You have to calculate the certified uncertainty. No value can be issued without an uncertainty. How well do you know the value? Then SED, the people with the power, they approve the statistical calculations, the methodology used. And then the technical division writes what we call a report of analysis, the official technical document, which is specified in this quality management protocol. And then there's a summary document called a project completion memorandum that summarizes all the work done, including the appropriate reports from SED and any other divisions that had input. Then we write a draft vision of the certificate, and then that is submitted with the whole package to the SRM division. They approve the final certificate, and then we calculate the price, and it goes out for sale. The certificate I showed before for the borax SRM, the certification measurements for the newest batch have been completed. The value is there, the certificate and all the paperwork is at this stage here, and right now the previous batch, the one I just showed here, is out of stock. You can't buy it. People are out there. We want to buy. We need the standard reference material to check our pH measurements at pH 9.2. And we're still waiting for it to come out. When it does come out, that certificate will have not my name on it, because it was finished, it was done after I retired. It will have Regina Easley and Jason Waters will be the people that did that measurement, and some of you remember Regina. This is the primary measurement method for pH called the Harned cell. Essentially, it's a battery. It's a battery, and the potential of the battery depends on the potential of the hydrogen electrode against a silver-silver chloride electrode here. Whoop. And the voltage, if you will, the potential difference of this battery is given by the NIST equation. If you combine the NIST equation and perform some 10th grade algebra, combining it with the definition of activity, ionic activity, which is the activity coefficient times the, in this case, the molality of the ion, you can get this equation, what we call a measurement equation here, where this is called the acidity function, which that's just the name of this. P is minus log 10. Minus log 10 of the acidity of hydrogen ion times the activity coefficient of chloride ion is the potential measured of this cell filled with buffer minus the standard potential of the silver-silver chloride electrode divided by the slope of the NIST equation, RT log 10 over F, gas constant, temperature, Faraday constant, RT and F, and plus the log of the, you add to the buffer, you have to add chloride ion as sodium chloride to poise this electrode, to determine the potential of this electrode here. When you do that, you extrapolate it back to 0, and you get the acidity function at 0 added chloride. If you then know the activity coefficient of chloride at trace chloride, essentially at 0 added chloride, in the presence of the buffer, then you can, using the algebra of logarithms, you have minus log of this product plus the log of this product gives you minus log of activity of hydrogen, which is the definition of pH. And this is the typical Harned cell that is used here, used at NIST. This part here, the purpose of this part is merely to humidify the hydrogen, bring it in equilibrium with water vapor so that the hydrogen that comes out here is not evaporating the solution in the cell itself. This is the solution in the cell itself, and you fill the cell. It's all one solution, but you need to avoid the hydrogen evaporating the solution and shifting the potential of the cell. That's why those compartments are on the right. And I might say here, for measuring pH of seawater, this cell can be used the same way. You don't do the extrapolation with addition of chloride to a chloride-free buffer because seawater is full of what? Chloride. So you have seawater, and then you have different additions of hydrochloric acid, and you extrapolate that back to 0. And then you have one measurement of seawater by itself, artificial seawater by itself, and then to determine the E0 star, the standard potential of this electrode, of the silver-silver chloride electrode in seawater, you have to add small amounts of hydrochloric acid, which is to poise the hydrogen electrode, this one here. This is seawater. Artificial seawater has none of the buffering carbonate and borate components that you have in seawater. It's just all the ionic components that are not acid-base, not weak acids and bases. The sodium chloride, potassium chloride, sodium sulfate. Well, that isn't really, the second proton is a weak acid, and that perturbs and makes much more difficult the calculations of the pH-T in seawater. And what, magnesium chloride, magnesium chloride, potassium chloride, sodium sulfate, and what's the fifth one? There's a fifth one, I forget what it is. Oh, what's that?
You didn't say magnesium.
Magnesium chloride, potassium chloride, sodium sulfate, sodium chloride, and what's the fifth one? No, I forget right now. There were five components you have to put in a buffer. There's a fifth one there. Okay, so that's the pH measurement. One thing to say about the measurement, you need to know, in order to get the acidity function, which you're plotting here to get the acidity function at 0, which you need to get the pH, you need to know the E0. How do you get the E0? You need to add, you measure this cell filled with a dilute solution of hydrochloric acid, typically 0.01 moles per kilogram. And you need to know exactly the molality. You can think of it as concentration, but it is molality. Molality is the amount of substance per kilogram of solid water, which if you know the amount of substance, the number of moles of hydrochloric acid per kilogram of solution, you know how much hydrochloric acid is, you can get to the molality. Those quantities have the advantage that over concentration, which is the volume-related moles per liter of solution, have the advantage that they are not temperature dependent. The volume changes with temperature. The mass does not change with temperature. So that's why for these very accurate measurements, you have to make sure that you are measuring a property that doesn't change or changes as little as possible with environmental conditions that you're doing, even if it's a temperature bath. Still, the bath has an uncertainty of what the temperature is. So you want to control all the variables as much as possible. So the E0, you need to know the amount content, the moles of HCl per kilogram of solution. How do you determine that? You do using this electrical titration called Kalamatree. Essentially, you are generating hydroxide on this side. The hydroxide neutralizes the H plus from the hydrochloric acid. This is just the other half of the electrode. It's silver going to silver chloride, so you don't get silver ions coming across here and precipitating out, because every electron that is reacting with water to give a hydroxide ion, you want to achieve the desired reaction and not be reducing silver ion to silver metal, because that would be a bias. That's a systematic error. That's why you have these intermediate compartments to keep the silver, any silver that is there, from getting across here. This is essentially Faraday's law of electrolysis. The mass of analyte, the molar mass of whatever you're analyzing, the current, the time, the equivalence per mole, the number of electrons taking part in the electrode reaction, or in the titration reaction, and Faraday's constant, which is what they call a universal constant. A universal constant is the same everywhere. And if you think back to physics, the quantity that you can measure most accurately is time. You can measure time to parts in 10 to the 15th. And the speed of light is one of these universal constants. If you know the time and the speed of light, then you can determine the meter. And when I came to NIST, the meter was determined in a different way, but in, was it 1993 or something like that, the definition of the meter was changed to the distance that electromagnetic radiation covers in a time period of 1/n seconds. So, and then the speed of light has a fixed value because it's an unchanging constant. And in the olden days, back in the days of the French Revolution, they had the kilogram, which was the mass of this platinum iridium cylinder, and then there was the meter, which was this H-shaped bar with two razor-thin marks on it. That determined the meter. But what if the bar gets dropped? Okay? If the bar, well, what if the kilogram gets dropped? If that's the standard for the whole world, if you change its mass, that's the standard. Everybody else's mass changes because you drop the kilogram. There is an effort now to redefine the kilogram in terms of, essentially in terms of physical and electrical universal constants. And that will be come into effect in the next couple of years. So that's the last one that's a physical artifact, not from 1793, but from the Treaty of the Meter was signed by all the participant countries, of which the US is one of them, in 1878. And the standard cylinder for determining the kilogram dates from then, and they've made replicas since then, and then the different countries have different replicate cylinders. The United States has number 4 and number 20. I've never seen them. I have seen the ones that were for the Czech and Slovak republics that were when I was there in the Slovak Republic in 1995. And interesting, what happened in World War II? Germany occupied France. They were at this site at the Bureau International de Poids et Mesures, the International Bureau of Weights and Measures. But Germany recognized by its treaty the BIPM and its overlay for all the what's called the Système International d'Unités, the International System of Units, the SI. That's the highest level of metrology, if you will, the fundamental units, and everything else derives from that. The primary methods are as close as you can get to the SI. Anyway, so that's coulometry. Coulometry has the advantage that it is the most accurate chemical analysis technique known. You can perform analyses that are good to parts in 100,000. In fact, Jason Waters just did some analyses of one of the primary substances, benzoic acid. And benzoic acid you can make in very high purity if you do it right, and if you have good material, you can determine it to within a few parts in 100,000. That's like measuring the distance from here to Washington with an accuracy of less than the distance from here to the other end of the room here. Titrimetry is what they call a primary ratio method. It doesn't. Coulometry takes a chemical quantity, takes it back to the electrical and physical values, time, current. Titrimetry, you always have to have a chemical standard, and you can standardize a standard B against standard A using a titrant. So it's a ratio method. It measures the ratio of B to A. And what we do, we never use burettes. Remember, volume changes with temperature. So everything is measured by mass. You add a concentrated titrant. This can be, if it's a very homogeneous compound, can be a solid sample and not a solution. And then you add about 98% of what you expect to be there. The last 2% you put in drop, 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 and measuring the mass of each drop, and then measure the potential of a endpoint detecting electrode. It could be a pH electrode for an acid-base titration. It can be a platinum electrode for oxidation reduction titration. And you get an endpoint curve, and then you model. The blue is a model minimizing the scatter of the experimental points, and then you can calculate the derivative and get where the endpoint is. And then if you know this, you know the reaction that takes place gives you the stoichiometry. The dilution factor is the ratio of the amount content of this one to this one, because you've diluted. This is lower than this. This is the, okay, I'm looking, this is the amount of substance here. Expressed in terms of amount of substance, this is true here. Number of moles. But number of moles, you don't say this is a mass. What is the number of kilograms? What's the mass of it? Not what is the number of kilograms. So for the mole, you don't say what is the number of moles. You say what is the amount of substance. And other uses, there's a nice metrological word, deprecated. Look, we don't want to express it that way. We don't like it. It's deprecated. Not a word you'll see. Maybe you can use it in a Scrabble game sometime. Electrolytic conductivity. The primary measurement method is what we call an absolute conductivity cell. There are two electrodes here. You put an alternating current across this and measure the alternating current potential difference between the two electrodes, but with the cell in two configurations. One with the tube in here, and number two with these two put together like this. You get two resistances measured that way. The different, if you design the cell correctly, if the electric lines of force are all parallel in this central portion, then from the diameter of this and from the length, you can calculate the conductivity of the solution from physical quantities and the electrically measured resistance. Not quite as easy. You've got impedance, you've got impedance factors, electrode capacitance, and stuff that you've got to take into account. But in principle, it's a useful and highly accurate method. Now you've made the measurement. How do you get the certified uncertainty? Remember, the value measured, you need to have the uncertainty also. You've got what we call the combined standard uncertainty of the primary method. That is all of the components that go into what we call the measurement equation, the equation that yields the measured value. For coulometry, the uncertainty in the time measurement, the uncertainty in the current, the uncertainty in the mass measurement. There's a small uncertainty in the Faraday constant. That has to go in there. There are chemical uncertainties, which are normally larger. You say that every electron makes this reaction, but if some of the electrons make a side reaction, I call that embezzlement of electrons. If that happens, then you have to take that uncertainty into account. Homogeneity of the certified batch is the scatter of all the values for coulometry. For pH, it's a little bit different because the Harned cell is a very labor-intensive measurement. So you cannot make a measurement of each and every bottle that you're going to use for the analysis with a Harned cell. It would take you years. So what we do is we make a glass electrode measurement of small aliquots from each bottle, and then we measure the scatter of that. That determines the homogeneity. The certified value comes out of the primary measurement, the Harned cell measurement. With coulometry, this is just the scatter of the coulometric titration results. The final result comes from SED. This, of course, is printed in red for reasons previously discussed. And if you don't know, then the secret police will inform you. Now you have to combine this uncertainty with this uncertainty, and uncertainties combine in quadrature, so the sum of the sum of squares, the sum of the squares take the square root. Then you have to calculate what we call the coverage factor. This behaves statistically like a standard deviation. So one standard deviation covers, about 68.3% of what you'd expect. If you want to get 95%, then you multiply it by what we call a coverage factor. The value of the coverage factor is determined by the degrees of freedom. And the degrees of freedom comes out of this equation here, coming from the combined standard uncertainty and the sum of those component uncertainties which have a specified number of degrees of freedom. Then if you know K and you know the combined standard uncertainty, you get the expanded uncertainty. This is what typically goes on the certificate. Traceability of the value for pH SRMs, the result of the primary method. And it goes back to the measurements of the potential, the temperature, the pressure, and to the molality of HCl from the coulometric determination. So that means if you're using a Harned cell to measure pH, you have to have traceability back to coulometry to know the molality of the hydrochloric acid. That's why Sherwood here is interested in establishing for seawater pH measurements a capability here at USF for coulometry, so that then the results of the Harned cell measurement for pH measurement of seawater can complete the traceability chain here. For coulometric SRMs, it's a primary method, the most accurate method